Hello, everyone. Our goal today is to talk about the fundamentals of state estimation in power systems. The objective behind state estimation, as the name says it, is to estimate the states of the power system, which for the most part consist of voltage magnitudes and phase angles at different nodes. Now, at this point, you might wonder, power flow tries to estimate the same thing, so why would we need yet another technique? Let's revisit what we learned about power flow. And as an example, let's consider this iterative equation, which was from Newton-Raphson technique. You remember that the states were defined as the phase angle for all the buses, as well as voltage magnitudes for all the PQ buses. The new values would be a function of old values plus the inverse of some Jacobian matrix times mismatch equations for active power and reactive power. And you also remember that we had the same number of equations as unknowns. Now, in this equation, if one of the measurements that I have, let's say one of the active power measurements, has some errors in it, this could be either a measurement error or a communication error. If I have some errors in it, through this iterative equation, that error will be propagated through the entire set of states. That means every delta value and every V value that you will find will have some errors associated with it. So in a sense, power flow is not robust against measurement or communication errors. In order to address that issue, we use state estimation. In state estimation, our goal is to increase the number of equations. So if I have an n total number of states, I would try to find m number of equations where m is greater than n. In other words, I would form the problem in the shape of an overdetermined set of equations. I will have more equations than unknowns. And then I'll try to find the set of system states in such a way that they statistically fit those measurements the best. Why do I say statistically? Because I have, again, an overdetermined set of equations. So the answer to this set of equations would not be exact. It would have to be an answer, state variables that would best match those measurements that I have. Let me give you an example. Imagine I have a system and I'm trying to measure the voltage at some point in this system. I want to know what the value is. And let's say I measure this voltage 4 times using 4 different techniques, or let's say I have 4 different voltmeters. And imagine I measure 120, 115, 115, 110. So these are the 4 measurements that I have. If I want to know what the value of the voltage is, and assuming that all these measurements have the same level of accuracy, my answer would be the value that statistically fits those measurements. The value that statistically fits 120, 115, 115, and 110 would be 115. So this would be my measurement. Notice that here again, I have more measurements than unknown. So my unknown, it would be just 1, whereas I would have 4 measurements. So it would be an overdetermined set of equations. What I'm doing in power system state estimation is exactly the same idea. I would include more equations than unknowns, and then I would try to find the set of V's and deltas that would fit those measurements statistically. The measurement model that I have in the most general sense would be nonlinear. So I would measure some things, which could be, for example, your active power, reactive power, voltage magnitude at a node, current magnitude, voltage phasor, current phasor, all these different things that you can measure. And these would be related to the states of the system through some equations h of x, which in the most general sense would be nonlinear. Now, again, remember that I have m measurements. So the vector of measurements would be m by 1, and I would have n states. So x would be n by 1, and of course, h would have to be the same dimension as z. Let's see this through an example. Imagine I have a two-bus system with nodes K and J. Here I have VK, delta K, VJ, delta J. And let's assume that this line has an admittance of YKJ. Notice whenever I use small letter, I'm referring to the actual admittance of the line. If I use capital letters, that would be the particular entry of the admittance matrix. And again, for simplicity, let's assume that the line does not have a conductance. So this admittance matrix is simply equal to the susceptance times J. Now imagine my states are, let's say, VK, delta K, and VJ. In this particular example, I don't include delta J as a state because you would have to set one of those angles as a reference. So I'm assuming here that delta J is 0, so delta K is going to be measured with respect to that. So these are my states. And let's assume what I'm measuring is I'm measuring VK, I'm measuring VJ, I am, let's say, measuring delta K, and I'm also measuring the active power and reactive power that goes from bus K to bus J. So these are my measurements. So that would be my vector of x's. This would be the vector of measurements, which is z. Let's see how these measurements are related to my states. In other words, let's see what that function h of x is. So here, my vk measured value, I put this m to indicate that this is an actual value. It's a measurement that I have. How is this related to my states? Well, my states are vk, delta k, vj, and this measurement is associated to the states in a very direct fashion, equals v of k. What I measure for the angle of voltage at bus k, again, how is it related to my states in a direct fashion? Vj would be the same way. So again, notice that these are my z's. These are the functions that relate z's to the states x's. Now we come to p, k, j. Recall that pk, the active power injected at bus k, that was for the Newton-Raphson technique, we found it as v of k times summation of, let's say, I goes from 1 to n of vi's, bki, and then sine of delta ki. And q of k, that was vk, summation of I, again, going from 1 to n, of vi, bki, and then here cosine of delta ki with a negative sign. So that's my pk, that's my qk. If I want to find pkj or, for example, qkj, the measured values, your initial thought would be perhaps that I find the entry within the summation for which I equals j, that's corresponding to bus j, and then I multiply it by vk. That would be correct for pkj because I will have vk, vj. Notice that I'm only looking into the term within the summation in which I equals j, bkj, and sine of delta kj, which I can actually write it as delta k minus delta j. For reactive power, however, things are a little bit different. So it's a subtle point that you have to pay attention. I'm going to break this down into two terms. So minus vk times summation of i's that goes from 1 to n of vi to bki. Notice I'm adding I is not equal to k, cosine of delta ki, plus the term associated with when I actually equals k. And that would be vk bkk cosine of delta kk, which is cosine of delta k minus delta k, and that would be cosine of 0, which is 1. I did not have to do this for active power because the corresponding term for active power would have been vk bkk sine of delta kk, where sine of delta kk sine of 0, which is 0, so that term would be irrelevant. But that term does exist when I'm looking into reactive power. Now, again, you might wonder, why am I doing this? The reason is, if you recall, the entry bkk of the admittance matrix was in fact nothing but minus summation of bki's. So it seems like I have a term within this summation associated to when I equals j, and also within this summation when I equals j. If I do that, my qkj is going to be corresponding to the first term would be minus vk vj bkj cosine of delta k minus delta j minus vk, and I have another vk here, so vk squared, and then the term within this summation corresponding to I equals j would be bkj, but notice I have a negative sign as well, which cancels this negative sign and becomes positive. So these would be the nonlinear set of equations that would relate my states, which are delta k, vk, and vj to my measurements, which would be the measured value for vk, measured value for delta k, measured value for vj, as well as measured values for pkj and delta kj. So again, this would be the vector of z's. These are actual values that you have. These would be the vector of h of x's. If you're directly measuring the state, obviously the relationship is going to be linear, just like here. But if it's not the direct state, then your equations would be nonlinear. Now, in the most general sense, we will have some errors associated with our measurements. We could have some errors associated with our function h of x because the values of the admittances, for example, may not be exact. We could have some communication errors. So even if I measure the particular value of voltage or active or reactive power correctly, once I transmit it to the control center, the value might be affected by noise a little. So in general, that equation z equals h of x will become z equals h of x plus e. So these errors would be individual errors associated with every single measurement. Now, I make certain assumptions about these errors of measurement. First, I assume that meters have no biases, meaning that they do not systematically overestimate or underestimate their measurement. Mathematically, this can be shown as expected value of the errors for every single meter would be 0. That means you could have positive errors or negative errors, but on average, the meter has no bias. In addition, I assume that the errors of different meters are not correlated with one another. For example, the fact that meter number 5 has a positive error of so much, it does not tell me anything about the error of meter number 1 or meter number 10 or whatever. And again, mathematically, I model this as expected value of the errors of different pairs of meters would be 0, which means that they are not correlated. Now, every meter itself is going to have a standard deviation of error, which would indicate how much these errors of measurements at different measurement instances disperse around 0. So If, for example, I'm looking at the error of measurement, let's say 0 means there is no error and the measurement is 100% exact, this would be an ideal case. But imagine you have a meter that's in one measurement, it has this much of error, so positive error, in another measurement has some negative error, another negative error, and then another positive error. Then I can define a standard deviation of error associated with this distribution of errors around 0. Now consider I have another meter in which one of the measurements has this much of error, one other measurement has this much error, measurement number 3 has this much error, number 4, number 5, number 6, and so on. This meter, as you can see, compared to the first meter, would have a larger deviation of error values. So the standard deviation of error for this meter would be higher, meaning that this meter number, let's say meter number 1, would be more accurate than meter number 2. And in order to model the accuracy of meters, we look into the standard deviation squared. I'm sorry, I keep hitting the enter key and I go to the next slide. So I look at the square of the standard deviation, in this case, sigma 1 squared, which in fact is my variance. And sigma 1 squared would be, in this case, less than sigma 2 squared, which means that meter number 1 is more accurate than meter number 2. Now, how do we solve the problem of state estimation? What we would like to know is, based on the set of measurements that I have, what would be the likely state of the system? Again, the V magnitudes and deltas that would fit those measurements. In order to solve that problem, I formulated in the form of weighted least square method. So I try to minimize the sum of all the residuals squared, where the residual for measurement number I is defined as the actual value measured minus the function that relates that measurement to the states. In an ideal world, if everything was exact, every residual would have been 0, because every measurement would exactly be related to the states through a very accurate and exact equation h of I. In practice, however, this is not the case. So there will be some difference between the actual measurement, what I measure in the field, and what my calculations will give me. And that's my residual, and I would like to find the x's in such a way that those residuals squared are minimized. However, notice that not all measurements are the same. The meters that have higher accuracy should be given higher priority, and conversely, meters that have very low accuracy and historically have had higher errors, these have to have lower priorities. So in order to prioritize different measurements, I assign a weight coefficient to every residual, and this weight coefficient for meter number I is inversely proportional to its variance of error. If you have larger variance or larger standard deviation of error, that means that the weight of that meter reading, the priority of that meter reading, would be lower. Now, the previous equation that I showed you, it's a quadratic form. It can be easily solved using any standard optimization solver. But typically in power systems, and I should say perhaps historically, we've been solving it in an iterative fashion using matrix calculations. So that j of x, my objective function, which I can write as summation of all the residuals squared divided by their corresponding variances, I can write this in the form of a quadratic matrix form, which is z minus h of x transpose times w times z minus h of x. Let's take a look at the dimensions of this equation. Z is m by 1, and likewise h is m by 1. When I transpose the whole thing, it becomes 1 by m. Matrix W is a diagonal matrix whose main diagonal entries are 1 over the variances for different meters. So 1 over sigma 1 squared all the way to 1 over sigma m squared, and these entries are 0. In fact, you can think of it as the inverse of the covariance matrix of errors. So this matrix is going to be m by m, and then obviously this is going to be m by 1. So collectively, 1 by m times m by m times m by 1, this will be 1 by 1, which is my objective function. In order to find the value of x's that will minimize this, I will find the derivative of j with respect to x and set it to 0. Now, think of this equation as a function u of x times a function v of x. Derivative of this with respect to x would be u prime v plus u v prime. So this would be derivative of this term with respect to x is minus derivative of h with respect to x transpose times v. So that's a u prime v, w z minus h of x, plus the first term now, which is u here, z minus h of x transpose, and times w times v prime. So the derivative of this term with respect to x, which obviously is minus derivative of h with respect to x. I have to add a transpose here in order to make sure that dimension of the first term is equal to the dimension of the second term, and I set the whole thing to 0. This obviously means that I have minus 2 times some matrix H transpose, which is essentially the derivative of H, times W times Z minus H of X. Now for this particular matrix H, pay attention that this is the derivative of the vector H, which is m by 1, with respect to all the x's that are n by 1. So the dimension of H would be m by n. This has to be 0. Obviously, I can ignore -2. So what I will have is H transpose of x times W times Z minus H of x is 0. This is a nonlinear equation. Think of it as some g of x. Now, you recall from Newton iterative technique that if I had an equation of the form, let's say g of x equals b, the iterative form in order to solve this would have been x at iteration nu plus 1 equals x at iteration nu plus derivative of g with respect to x inverse times b minus g of x. This is the same equation, except that in this case, b equals 0. So my iterative equation becomes x iteration nu plus 1 is equal to x iteration nu plus derivative of this guy with respect to x, which becomes H transpose WH inverse, times b, which is 0, minus g of x, which again is this function. When I find the derivative, there is a minus sign in the derivative. There is a minus sign here. So those two minus signs cancel each other out, and you're going to have a plus sign here. So the general equation is going to be x iteration nu plus 1 equals x iteration nu plus this matrix inverse times this. Now, before I show you one example of how this is solved, let's go back to matrix H and see how we would find it. Let's consider the previous example that we had. So our general form of z equals h of x was, I had, if I remember correctly, I had vk measured, delta k measured, vj measured, and then p kj, q kj. So that was my vector of z's. And this was basically vk on the equation side, delta k, vj, and then I had what, vk, vj, bkj, sine of delta kj, and here I had minus vk, vj, b kj cosine of delta kj plus vk squared b kj. Let's say, again, my states, I assumed that delta J is 0 is my reference. So my states, usually we have deltas on the top and V's at the bottom. So that would be delta K and then Vk and Vj. Okay. Now, if I want to find matrix H, remember that H is the derivative of all the H equations. So think of this as H1 of X, this one as H2 of X, this one H3 of X, H4 of X, H5 of X. And obviously you can imagine this is Z1, this is Z2, all the way, this is Z5. So the matrix H will be derivative of H, all the H's with respect to all the X's. So let's go ahead and form that matrix so you know how you would have to find the entries of that matrix. The first row of matrix is going to be, so if, let me start here, and then I go back to that matrix and try to fill it out. So that matrix is going to be D of H1 with respect to X1, D of H1 with respect to X2, D of H1 with respect to X3. Again, notice that this is X1, this is X2, this is X3. And you continue D of H2 with respect to X1, D of H2 with respect to X2, D of H2 with respect to X3, and then you continue, right? So let's look at my H1 of X, which is just Vk. Derivative of that with respect to delta K is 0. Derivative of that with respect to Vk is 1. Derivative of that with respect to Vj is 0. Let's come to H2 of X. Derivative of H2 of X, which is delta K, with respect to delta K is 1. With respect to Vk is 0. With respect to Vj is 0. Derivative of Vj, which is H3 of X, with respect to delta K is 0. With respect to Vk is 0. With respect to Vj is 1. These are pretty trivial, but the ones that we have to work on a little would be equations for Pkj and Qkj. So let's consider H4 of X now, which is Vk, Vj, Vkj sine of delta Kj, which of course you can think of it as delta K minus delta J. What is the derivative of this with respect to delta K? Derivative of sine with respect to delta K would be cosine. So you have Vk, Vj, Bkj cosine of delta. Let's write it as delta K minus delta J. Derivative of H4 with respect to Vk will be Vj, Bkj, sine of delta K minus delta J. And again, here I'm assuming delta J is 0, so it's really irrelevant, but I'm leaving it in the equations for completeness purposes. And that derivative with respect to Vj is going to be Vk, Bkj, sine of delta K minus delta J. Let's go to the next one. So for H5 of X, which is corresponding to reactive power, that derivative with respect to delta K, derivative of cosine with respect to delta K would be minus sine, so the minuses cancel out, and you're going to have Vk, Vj, Bkj, sine of delta K minus delta J. The second term has no delta in it, so the derivative of that with respect to delta will be 0. Derivative of H5 with respect to Vk will be minus Vj, Bkj, cosine of delta K minus delta J, plus 2 times Vk, Bkj. And then the derivative with respect to Vj is just going to be minus Vk, Bkj, cosine of delta k minus delta j. And again, the second term has no vj in it, so the derivative would be 0. So this matrix is going to be my H matrix. And again, remember that this is m by 1, this is n by 1, making H m by n. I have 5 measurements and 3 states, and notice how this matrix is 5 by 3. Now, the rest of it is going to be pretty straightforward. You calculate your H, you have your W, and essentially what you do is you start from X iteration 0, which is all the V's typically 1 per unit, all the deltas are 0. So you plug in those values here, evaluate H at those values, transpose it, multiply it by W, evaluate H, and then invert the whole matrix times this. And again, notice that this is what you calculate and evaluate at X. W is a constant matrix. Z is a vector of given measurements, and H's are again the nonlinear relationships between the states and the measurements, which you would have to evaluate at X of V. So you have X of 0, plug in those values, you find X of 1. You plug in the values for X of 1, you find X of 2, and you continue until your threshold of error has been met, meaning that your values of your states have converged. In a special case where the relationship between the states and measurements is linear, things are going to be much, much easier. So here, instead of having z equals a function h of x, it's going to be in the form of some constant function matrix h, times a vector of x's. And your objective function becomes z minus h times x transpose times w times z minus h times x. We do the same thing, essentially. We find the derivative of that with respect to 0. If you repeat the calculations I showed you earlier, you will get an equation like this: h transpose w z minus h times x equals 0. Notice that this is a linear set of equations. Because it's not nonlinear, we do not have to find an iterative solution. So the solution to this would be direct, and it would be something of this form. That would be the solution to the linear case. The linear case, for the most part, happens when matrix H is consists of all constant parameters, and typically that happens when your measurements are the direct state measurements. So when you directly measure your V's and deltas, your matrix of H is going to be a matrix of constant coefficients. Now, before we conclude this topic, I wanted to talk a little bit more about the states. In the beginning of the presentation, I mentioned to you that the states, for the most part, are V's and deltas at different nodes. There are some exceptions. So sometimes we run into situations in which we have to identify additional variables as states. One example is if you have a transformer with a tap changer, the tap position would also have to be a state, and you would do exactly the same thing that I mentioned. You would have to include the tap position T in your equations, and find those nonlinear equations h of x's, find the derivatives, and repeat the whole thing just like you would for another standard state of voltage magnitude or phase angle. There are some other situations as well. Imagine you have two buses that are connected to one another through a circuit breaker. Notice that even if I know the voltage phasor here and voltage phasor here, I'm not going to be able to calculate the powers that are going through the different phases of the circuit breaker. The reason being that this circuit breaker does not follow Ohm's law. So essentially, I cannot write a KVL for this path. So in a situation that you have simply a circuit breaker connecting two buses to one another, the power that is going through the circuit breaker and the reactive power that is going through it, or perhaps the current, these would be defined as additional states as well. So this brings us to the end of this presentation. There's a lot more to state estimation than we covered in this short presentation, but hopefully this gave you a better idea of how, at least for the simple case, we can formulate state estimation and solve it using the weighted least square method.